In this recording, we're going to get to matrix multiplication, which we'll look at from 3 viewpoints. First, we'll cover 2 of them, then we'll talk about the outer product in vector multiplication, and we'll wrap back around to matrix multiplication. Or perhaps one of the most important things to take away is that matrix multiplication is not commutative. AB is not equal to BA. Matrix multiplication is only defined for dimension-compatible matrices, and that dimension compatibility is actually order-specific. Let's talk about this. If A and B are dimension-compatible, then we can compute the product AB by multiplying every row of A by every column of B, taking inner products. And the ijth entry of the product is the ith row of A multiplied by the jth column of B. Now, this is a lot easier to see when we illustrate it. Again, here I have a green matrix A, a purple matrix B, and the product AB. First, let's talk about dimension compatibility. If we write down the dimensions of A and B, A is 4 by 3, B is 3 by 4. The first thing we need to do is check that what we call the inner dimensions agree. That's the number of columns in A and the number of rows in B. I always refer to them as the inner dimensions, again, because they are on the inside of this expression here. If those inner dimensions agree, then we look at the outer dimensions, and those become the dimensions of our product. So our product is 4 by 4, precisely because A has 4 rows and B has 4 columns. That just tells us about the size of the matrices, or the size of the product. Algebraically, the way that we'd write this product is as follows. The ijth element of A times B is the ith row of A times the jth column of B. Visually, for example, if we wanted to find the 2, 3 element of A times B, I would multiply the second row of A times the third row of B. And again, this is an inner product. So we'd multiply each corresponding element and then add to get the single element in the product. Matrix multiplication is just a big collection of addition and multiplication operations in one step. Let's look at some examples. Here I have 2 matrices, A and B. To multiply them, I'd start by checking their dimensions to make sure they're even compatible. When I do that, I see that the inside dimensions do match. So the columns of A is the same as the number of rows in B. And then I know that the resulting product will have the outside dimensions, here 3 by 2. Of course, if these do not match, then the product is not defined. Finally, in order to get the product, I have to multiply row times column, row times column, row times column. I used to have my undergraduate students repeat row times column, row times column, because when you deal with matrices, that row coming first comes up quite often. For example, when you specify the size of a matrix, it's the number of rows first. When you specify an element in a matrix, you specify the rows first. And when you multiply 2 matrices, you always multiply rows of the first by columns of the second. Again, matrix multiplication is just a lot of multiplication and addition. Final result here after performing all of the computation. Here's a good place to stop and check your understanding. All you have to do is determine whether or not these matrix products are possible based on the dimensions. And once you're done, come back to the recording and you'll see the solution. Here's the solution. Here's another place to check your understanding where you'll actually compute some matrix products. Again, pause the recording. When you come back, you'll find the solution. Here's the solution. Again, it's very important to remember that matrix multiplication is not commutative. As we see in the previous exercise, it's quite common to be able to compute the product A times B when that reverse product, B times A, is not even defined. Even when both products are possible, it's almost never the case that AB is equal to BA. Next, we'll look at some special cases of matrix multiplication, the first being multiplication by a diagonal matrix. Here I have a diagonal matrix. Remember, diagonal just means that I have all zeros that are not on the main diagonal, the II entries. And I have a matrix A. And the question is, what happens when I multiply D times A? Well, let's think about getting this first row here of the product. To get the first row, I take this first row of D and I multiply it by the first column of A, and then I multiply it by the second column, and then I multiply it by the third column. So when I do that, it's almost like I pick up this row of D and I turn it on its side and I push it through A. Now these zeros are always going to line up with the bottom two rows of A, and the 2 is always going to multiply the first row. So when we do this, I really just get 2 times 1 plus zeros, 2 times 2 plus zeros, 2 times 3 plus zeros. And so the result of D times A is 2 times that first row of A. And then when I carve out the second row, same thing is going to happen. But now I take the second row and it's a 3, and when it multiplies through A, I'm going to get 3 times the second row of A. And if you can't see that here just from looking at it, I suggest that you write down this calculation and perform it yourself until you become convinced that when I multiply this diagonal matrix times A on the left-hand side, the result is a scaled version of A. So for instance, I've highlighted that here. In order to get the second row of the product, I end up taking 3 times the second row of A. The net effect is that the rows of A are scaled by the corresponding diagonal elements of D. Now, what happens when I multiply D on the right-hand side? And I'm going to leave this for you to think about or to perform this multiplication. And this is one of the exercise questions on a worksheet. Now we'll take a look at matrix multiplication from a different point of view. Again, nothing changes with the underlying math. The formula and the way the computation is done will still produce the same result. It's just in the way that we represent all of those multiplications and additions that are happening. In this view, we look at matrix multiplication as a collection of matrix vector products, or linear combinations, as we've already seen, with different coefficients. Each linear combination will involve the same set of vectors with different coefficients. Let's see what we mean with a visual representation. We've already looked at how to multiply this green matrix by this purple matrix to get the result. For instance, to get the 1 element of the result, take the dot product or the inner product of the first row times the first column, and that will give me this 1 element of the result. A different way to view that is to realize that to get the first column of the result, what's happening is I'm really taking the entire green matrix and multiplying it by the first column of the purple matrix. Now, you can already see nothing changes in the underlying algebra because the way that this multiplication works is I multiply row times column, that's that element, second row times the column, gives me the second element, third row times the column gives me the third element, and I'm just doing the multiplication that I would normally be doing to carve out this first column of the result. But realizing that this is what's going on underneath allows me to think, just like we did with matrix vector multiplication, it allows me to think about this as a linear combination. Because those elements in the first column of the purple matrix become the coefficients on the green vectors in order to give me this first column of the purple matrix. Similarly, to get the second column of the resulting matrix, I use the second column of the purple matrix as coefficients. Same thing for the third column and the fourth column. This may seem like I'm just manipulating things, which I am, but the reason why I try to emphasize this as much as possible is because this view of matrix multiplication will really help us understand the different components or the different outputs that we get from a principal components analysis, which is one of the main analytical tools that we'll try to get to the bottom of using linear algebra. Again, matrix multiplication is just a collection of matrix vector products using different coefficients. Each of those linear combinations involves the same set of vectors, those are the green columns, with different coefficients, those are the purple columns. And like I said, this has important implications, but we won't see that until the fall semester. The final type of multiplication we'll cover is the vector outer product. The vector outer product is when we multiply a column vector times a row vector. And for any column and row, this product is possible. And the result of the product is a matrix. So again, it's always possible because a column times a row will always have the inner dimensions agreeing because they're 1. And so the result will be a matrix. It will be the number of rows in the column vector and the number of columns in the row vector. So let's take a look at this with an example. Here I have a column B multiplied by a row, A transpose. The result is B A transpose. This works just like matrix multiplication. I'm going to go through and multiply row times column, row times column. It turns out that those computations are pretty simple because they're just scalar numbers. The row is 1 number and the column is 1 number. So to get the 1, 1 element here, I multiply the 1, 1 elements. Similarly, to get the 1, 2 element, I multiply the highlighted purple and green elements. And to get the last element, that would be the last element in B and the last element in A. So an outer product is a collection of scalar products, really. Let's look at an example with numbers. Here I have two vectors, x and y. They have the same size, but that doesn't matter here because, again, the inner dimensions will always match. So when I multiply x, y transpose, you can see 3 times 1 is 3, 3 times 5 is 15, 3 times 3 is 9, 4 times 1 is 4, 4 times 5 is 20, and so forth. Now, what you might notice about this is that the rows of the product are going to be scaled versions of the y vector here, because this first row is 3 times y. The second row is 4 times y. And the last row is minus 2 times y. So you can see that the rows of an outer product are necessarily multiples of each other. For instance, this first row will be the first purple element times the entire green row. The last row will be the last purple element times the entire green row. And so therefore, these two red rows will be constant multiples of each other. The final view of matrix multiplication will be as a sum of outer products. And this is one of the more complicated ways to think about matrix multiplication, but it can be very useful. And I'll show you one example where I've had to use this in practice to run some efficient coding. And we will also see this pop up when we look at the singular value decomposition in the fall. And the straightforward way to write this algebraically is that the product AB can be written as the sum of all of the outer products using columns of A and rows of B. Now, again, in order to multiply A times B, it must be that the inner dimensions agree. So there's n columns in A and n rows in B, and that is the number of items in this sum. So we end up adding together n matrices, right? Because each outer product is a matrix. So I'm adding up n matrices in order to get the product AB. Now, in case you have some familiarity with this, each matrix has rank 1. We'll discuss this later. What that means really is that same fact we talked about before, that each row is a multiple of the other rows. That means the matrix has rank 1. But we'll get more into that later in this course. Now, using that fact, I'm going to propose this challenge puzzle. And I'll include this with the exercises, so I'm not going to go through it in too much detail right here. But suppose we have 1,000 individuals that have been divided into 5 different groups each year for 20 years. So every year they're randomly divided into 5 groups. And we want to make a 1,000 by 1,000 matrix, call it C, where the ijth entry is the number of times that person I is grouped with person J. The third bullet point here describes how the data is currently available, and we'll want to think about how we can use what we've just learned to help us make this matrix efficiently. Again, I'll cover this puzzle in more detail, but I wanted to propose it now in case anybody wants to think about how they might set this up immediately after thinking about outer products. Finally, we'll look at some special cases of matrix multiplication. In particular, we'll be interested in the identity matrix and the inverse matrix. The identity matrix, which is always written as I, is to matrices what the number 1 is to scalars. You may remember that 1 is the multiplicative identity. And for matrices, the identity is the matrix of all zeros that has ones along the main diagonal. And sometimes we specify the size. Here I have I4, meaning it's the 4 by 4 identity matrix. But for any matrix or vector A, multiplying A by the appropriately sized identity matrix on either side does not change A. So A times I and I times A are both equal to A. Just like the number 1 in scalar arithmetic, right? 1 times any number is that number. And that's why it's called the identity. When it comes to the matrix inverse, it turns out that certain square matrices, A, have an inverse matrix, which is written A inverse, where multiplying A by that inverse matrix gives you the identity. And it doesn't matter on what side of A you multiply the inverse, you still get the identity. Now, a matrix must be square to have an inverse, but not all square matrices have an inverse. Only full rank square matrices are invertible, and we'll talk more about rank later. But it's important, very important to realize that not all matrices have an inverse. For now, what I want you to understand is that the inverse matrix serves like the multiplicative inverse in scalar algebra. Now, you may or may not remember in high school learning this notation for the reciprocal. So 2 times the inverse of 2, or the reciprocal of 2, is equal to 1. This number, 1/2, is the inverse of 2, because when you multiply 2 times its inverse, you get the multiplicative identity. And that's the same thing that's happening here. When I multiply a matrix by its inverse, I get the multiplicative identity. Just some terminology. A square matrix which has an inverse is equivalently called either non-singular or invertible or full rank. Now this gets at a very fundamentally important difference between scalar algebra thinking and linear algebra thinking. For instance, in scalar algebra, if you had an equation that looked like this, you might be tempted to cancel that x variable from both sides. The problem with that here is, let's just look at the notation first, right? This is a matrix. X is a vector. Lambda should be a scalar, right? Because it's Greek and unbold. And then x is a vector. So if I were to cross out the x's here and say that a equals lambda, that doesn't even make sense because a is a matrix and lambda is a scalar. So writing a equals lambda is complete nonsense. When you're used to doing this in scalar algebra, what you're really doing is not crossing out numbers. Crossing out numbers is not an operation, right? What you're doing is you're multiplying both sides of the equation by the inverse of, in this case, 2. And when I do that, I get the multiplicative identity, which we rarely write down once we do enough examples because it's a waste of ink. Because 1x is just x, and 1y is just y. So the same thing holds true when we cancel matrices in linear algebra. If I have an equation like ax equals b, and I want to solve for x, the way that I might proceed, if I have an inverse, is to multiply both sides of this equation by the inverse of a, just like I did up here, to get rid of that 2. And when I do that, when I multiply a matrix by its inverse, I get the identity matrix, which will isolate x on this left side of the equation. And so there I've solved for the unknown vector x. So inverses can help us solve an equation when they exist. Again, not all matrices have inverses.